So we are going to continue where we just had previously how we could somehow see how what we can construct quantum reality fundamentally. So there were various what I should say relative interpretations, alternatives rather, how we could talk about the same, and in the particular case of this medieval interpretation which we are trying to follow is that we have to take not only observer the apparatus as well as the environment. A wave function, the construction of wave function is construed as if the role and play of all these things into while what we construe fundamentally as wave function. So the mathematical language is which we have to invoke before we are going to come to the point is probability theory as well as information theory. So mix of both. So the tools and techniques or the constructions of information theory in admixture of quantum mechanics or in admixture of probabilities, how we define probabilities. Because a probability, the theory of probability in itself is very vast. We have distributions, we have variance, we have covariance, and statistical variance. So how we are going to employ the constructs of probability as well as information theory in order to express that wave function, which is or state psi, where a role of all the probabilities can be taken into account of. So, for example, in a sense, for example, we can have one is the qualitative aspect. So, if you want to be quantitatively express the same, so notion of sharpness or definiteness of an operator A, of an operator A for psi and degree of correlation of subsystems. So last part of the lecture was that how the relative subsystems, which are which how they can be correlated. Those relative subsystems, they may themselves be in the sort of evolution. So you have to see how the correlation of subsystems are related with the notion of the sort of operator for psi. For a particular state psi, an operator is going to allow it to take a certain value. That value may be a discrete value or that may be a continuous value, which will be spanning a certain distribution, probability distribution. And that probability distribution can be both for discrete states as well as continuous states. So the probability distribution, which is to be what I should say, which spans a certain range of values, has to be seen vis-a-vis these what I should say subsystems, how the relative their co-evolution with these relative subsystems, that has to be taken into consideration. And you can say or degree of correlation of subsystem between of subsystems between the degree of correlation between the subsystems of a composite system or between a pair of operators in the subsystems. So we'll see how we can borrow the constructions of information theory and this thing in our today's section, which will say how probability, information, and correlation. So we have to correlate these relative subsystems and a particular interpretation of probabilities. How we can relate information with our understanding of probability, and how we can correlate these relative subsystems, which may themselves be in the evolution, a sort of evolution. So mathematically, it will be in a sense we have to, in first part of it is before coming to how we can arrive at things, how we can interpret, or how we can correlate things in some physical or concrete way. We have to first just be accustomed to or familiar to the language of probabilities. We'll try to somehow see how can the language of probability before coming to that thing. So we have to be see what I should say. So these probability distributions may span not only a range of, they can span a finite set of values or arbitrary set of values or infinite set of values, which depends upon the probability models which we are going to construct. So, for example, in our case, which we will develop definitions and properties of information and correlation for distributions over finite sets, only in the sense, and then we can go for arbitrary sets and see how we can prove general covariance of the correlation vis-a-vis those variables. So in the first place, you can have finite joint distributions. So which can include both marginal as well as conditional, what I should say, distributions in that sense. So for finite distributions, we can have a collection of finite sets, x, y, z, whose elements are denoted by x1 belonging to I, y1 belonging to y, z key belonging to z, etc. And for joint probability distributions, P, we can have P goes to xi, yj, zk, defined by the Cartesian product of sets which represent probability of combined sets, combined sorry events xi, yj, so on and zk, and we can denote random variables whose elements are of the sets x, y, z with probability given by p. So for any subset y going to z and set of random variables w going to x, going to y, going to z with joint probability distribution, P, we can define a marginal probability distribution as. So we are going to rehash some of the ideas of probability, which include conditional probability, marginal probability, joint probability, because these constructs are have to be how we can relate them later. So the marginal distribution is defined by. So in marginal distribution, we are interested in those variables which can little mod out or they are not part of that main thing. So marginal distribution. So you have this probability and this marginal distribution is defined as sigma going to j probability of so which represents probability of joint occurrences. Occurrences yk zl and no restrictions on remaining variables. So we can define marginal distribution like this. So we are interested in only on these set of variables, and we are not interested in the no restrictions on the remaining variables. In the same sense, we are going to define now conditional distribution, which depend upon conditional distribution of random variables. They depend on values, for example, w is going to for any remaining subset and denoted by condition depend upon the values this for any remaining subset and denoted by this is defined to be. So in the margin, we are interested in this set of variables and no restriction on the relative variables. In the conditional distribution, we are, which is defined as. So in the conditional distribution, we also have this idea of marginal distributions in the definition form of it. So probability of xj zl. So this is one set of variables. This is another set of variables. They have to be defined as wi, xj. These variables, this is sort of joint distribution, and the role of marginal distributions which come in the denominator. Where you can say probability of the joint event y is given by, so this is probability of joint event which is given by y k z, conditioned by the fact that w goes to x is known by the values, is known to have taken values from this wi to xj. So for numerical values, valued functions defined by the elements of the Cartesian product y, z, chi, from which those elements belong. So we can denote, we can have Cartesian product y, z. So we can have an expectation. E of expectation of f. F can be denoted as goes to L. Probability of yk goes to zl, and yk and we know that this probability is a marginal distribution. Of some larger distribution, which is basically larger distribution which we have defined P in terms of both x's and y's. So you can say a probability of wi x, this is xj, and yk goes to zl. Then this expectation can be defined as expectation of f can be defined as k goes to L L goes to G, sigma of probability of omega y, this goes to xg, and y key goes to zl. This is f of y key goes to zl. So you can have this, you can write it in a joint way. So if we have symbols k and l, and this is symbols k and l and j. So you can have this, if you combine these two, it goes I to j and k to l, can be written as probability of this xg yg goes to zl f of y key zl. So this is the way we have defined expectation f. Now if we wish to compute expectation with some vis-a-vis some joint distribution, we can use these marginal distribution of the original distribution. So we can also be occasionally interested in the conditional probabilities or conditional expectations. That's it. And the idea of mutual independence, or the way, if you remember, or you can see this thing, how probabilities, two individual probabilities, how they can be related when probabilities of two variables, how we relate them probabilities of their individual variables. So the same thing can be seen in terms of something called before we can just say there is something called conditional expectations, but this is expectation in the general sense. So conditional expectations means you are going to just define your expectations in a certain way, constrained way. In the same way, we can come up to the idea of something called notion of independence. Notion of independence. So two random variables. Random means it can take any value randomly, as language says. X and Y with joint distribution. P of xi yj is said to be independent. If probability of xi yj, if it's said to be independent, if and only if it is equal to, or if it's equivalent to probability of xi, probability of yj. So this is how we can define probabilities for joint distribution. So similarly, in the group of random variables, u w goes to and y goes to will be called mutually independent groups if and only if probability of ui, vj, wk is always equal to is always equal to probability of vj, probability of, so this and this is individual x and l, probability of this. So if I write one sentence further, which says that what further independence means. Independence means random values random variables take on values which are not influenced by other variables, influenced by other variables with respect to which they are described as independent. So conditional distribution of one of the two independent variables y is conditioned upon the value of other is independent. So this means knowledge of one tells us nothing about the knowledge of the other variable. So we'll stop here, and in the next we are going to talk about how we can see information for the finite distributions. That will be part of the next class.